Welcome to today's session. In this problem, we'll explore an interesting programming challenge titled Accepted LeetCode Problem Titles and Content Are Not Part of My Training Data. Together, we'll break down the problem, analyze various approaches, and discuss the most efficient solution. Let's dive in. In this problem, you are tasked with validating a string against several criteria to determine whether it meets the requirements for a hypothetical LeetCode problem title or content. Specifically, the string must include at least one uppercase letter, one lowercase letter, one digit, and one special character, where special characters are limited to the set at $% and asterisk dash plus equals. Additionally, the total length of the string must fall between 8 and 20 characters, inclusive. If all of these conditions are met, you should return true, otherwise, return false. The input is a single string, s, with a length ranging from 1 up to 10,000 characters. The output is a Boolean value indicating whether the string satisfies all the criteria. Now, let's look at an example to understand this better. Suppose the input string is s equals LeetCode at 123. In this case, the output is true. Here's why: the string contains at least one uppercase letter, which is the L, and at least one lowercase letter, like the E. It also includes at least one digit, such as the 1, and one special character, which is the at. Finally, the length of the string is 12, which falls within the valid range of 8 to 20 characters. Since all the conditions are satisfied, the result is true. Let's take a look at another example. If the input string is s equals LeetCode 123, the output would be false. While this string does include at least one lowercase letter, such as the L, and at least one digit, like the 1, it fails to meet two critical criteria. Specifically, the string does not contain any uppercase letters, and it also lacks a special character. Although the length of the string, which is 11, is valid, the absence of these other required elements means that not all conditions are satisfied, so the result is false. To further expand on this, the string LeetCode 123 also highlights the importance of meeting every single criterion. While its length is appropriate, and it contains both lowercase letters and digits, the lack of an uppercase letter and a special character means it cannot be considered valid according to the rules. Let's look at yet another example. If the input string is s equals short 1, the output is also false. In this case, the string contains one uppercase letter, the S, one lowercase letter, the H, one digit, the 1, and one special character, the. However, the total length of the string is only 7 characters, which is less than the minimum required length of 8. As a result, the string fails to satisfy all the conditions, and the output is false. This pattern continues with strings that meet most, but not all, of the criteria. For example, in the case of short 1, the string satisfies the requirements for uppercase letters, lowercase letters, digits, and special characters, but its length of 7 characters renders it invalid. The constraints for this problem emphasize that the string must meet all 5 criteria simultaneously. These include both the content-based checks like the presence of uppercase letters, lowercase letters, digits, and special characters, as well as the length requirement, which must be between 8 and 20 characters inclusive. Finally, let's consider some edge cases. A string consisting of only one type of character, such as AAAAAA, would fail because it lacks uppercase letters, digits, and special characters, and is also too short. A string like A1, might meet all the content-based criteria but would fail due to its short length. Similarly, if you extend that string with an excessive number of characters, like A1, followed by 10,000 AS, it would fail for being too long. Another interesting case is a string containing only special characters, such as at $% and asterisk. While it does include special characters, it would fail because it lacks uppercase letters, lowercase letters, and digits. These examples illustrate how each criterion plays a critical role in determining whether the string is valid. When tackling this problem, it's important to evaluate several approaches that could address the string manipulation or analysis tasks effectively. The brute force approach is often the most straightforward starting point. It involves systematically examining all possible substrings, characters, or patterns within the string, depending on the problem's requirements. For instance, if we need to find a specific substring or validate the string against certain rules, we can use nested loops to iterate through the entire string and explore each possibility. While this method is simple to implement, its inefficiency becomes apparent with larger inputs, as its time complexity is typically n squared, or worse. Next, we can consider a more structured strategy, such as hashing or frequency counting. In scenarios where identifying unique characters, counting occurrences, or validating constraints is required, this approach shines. By traversing the string once to populate a hash map with character frequencies, we can then analyze the data to solve the problem. This significantly reduces the time complexity compared to brute force, making it a much more scalable option for larger inputs. The hashing or frequency counting approach operates with a time complexity of n, since the string is processed in a single pass, and a space complexity of k, where k represents the number of unique characters, which is generally constant for English letters and digits. This efficiency makes it a powerful tool for most string analysis problems, though it does require additional memory for the hash map or frequency array. Another efficient strategy is the sliding window or two-pointer technique. This method is particularly useful for problems where analyzing substrings or dynamic windows within the string is necessary. By maintaining two pointers to define the window, we can adjust the size dynamically based on specific constraints, avoiding the need to restart iterations. This approach ensures that each character is processed at most twice, leading to a time complexity of n, with minimal space requirements. However, it does require careful implementation to handle edge cases effectively. Finally, regular expressions, or regex, offer a concise way to validate strings against patterns. Using libraries like Python's re module, we can define and match patterns efficiently. While regex is typically n, for simpler patterns, its complexity can vary based on the pattern itself. It's a powerful but less versatile tool for certain scenarios, particularly when patterns grow complex and harder to debug. Given the open-ended nature of this problem, selecting a strategy that balances efficiency, simplicity, and adaptability is critical. Among the approaches considered, the sliding window technique stands out as the most suitable option. It avoids the inefficiencies inherent in brute force while requiring less memory than hashing or frequency counting. The dynamic nature of the sliding window approach makes it particularly well-suited for problems involving substring or sequential analysis. While hashing remains a viable alternative for tasks such as validating character counts or uniqueness, it can introduce unnecessary memory overhead for scenarios that do not require such detailed tracking. On the other hand, brute force, despite being straightforward, is impractical for larger inputs due to its prohibitive time complexity. As with any approach, the sliding window method does come with trade-offs. Edge cases such as empty strings or non-alphabetic characters must be addressed carefully, but these challenges are manageable with appropriate checks and validations. For problems that demand flexibility and efficiency, the sliding window technique provides a robust solution that balances all these considerations effectively. The sliding window technique is an ideal choice because it offers an n solution, striking a balance between minimal time and space complexity. Its adaptability allows it to handle a wide range of string-related problems, from analyzing substrings to meeting specific constraints dynamically. This method stands out for its ability to process large inputs efficiently without the overhead associated with other approaches like hashing. Additionally, its simplicity in implementation makes it both accessible and powerful, provided that edge cases are handled with care. Overall, the sliding window's efficiency, flexibility, and broad applicability make it the optimal strategy for solving this problem effectively and elegantly. To begin solving any algorithmic problem, the first step is to thoroughly understand the problem itself. This means analyzing the problem statement to identify the input, constraints, and the desired output. For instance, is the task about manipulating strings, processing arrays, or traversing graphs? If the problem hints at optimizing performance, it's crucial to weigh the trade-offs between time and space complexity upfront. Once you understand the problem, the next step is to break down the input. Identify the type of input you're working with, whether it's a string, an array, or perhaps a tree structure. Additionally, consider edge cases like an empty input, or inputs with minimum or maximum sizes, as these can significantly affect your approach. Finally, define the exact outcome your solution should produce. This might be a single value, such as the maximum sum or a count, a modified structure like a sorted array, or even a Boolean indicating whether a condition holds true. By clarifying these details, you lay the groundwork for a structured and effective algorithm design. Once the problem is understood, the next step is to choose the appropriate approach. Depending on the problem type, you might start with brute force, which involves enumerating all possible solutions. This is often the simplest approach but may not be feasible for larger inputs. To improve efficiency, you can explore optimized iterative techniques like the sliding window or two-pointer methods, or even binary search. For problems that can be divided into smaller subproblems, recursive methods or divide-and-conquer strategies, such as merge sort or quicksort, are effective. If the problem involves overlapping subproblems, dynamic programming techniques like memoization or tabulation can greatly reduce redundant computations. After deciding on the approach, implementation begins. Start by initializing any necessary variables or data structures, like pointers, counters, or hash maps. As you iterate through the input, maintain invariants, conditions that must remain true throughout execution, while dynamically updating variables as needed. Ensure you validate conditions during iterations or recursive calls and store intermediate results if required. Finally, return the output as specified. This structured process ensures the algorithm is both correct and efficient. After implementing the algorithm, it's vital to handle edge cases. Test your solution against scenarios like empty or null inputs, single element inputs, and boundary values such as maximum or minimum constraints. Unusual but valid cases, like arrays with duplicate elements, should also be considered to ensure robustness. With edge cases accounted for, analyze the algorithm's complexity. Start with time complexity, evaluate how the number of operations scales with the input size. For example, does it run in linear time, logarithmic time, or quadratic time? Similarly, assess space complexity. Determine if additional memory is required, such as auxiliary data structures, or if the algorithm operates in place. If possible, optimize further by reducing complexity without compromising correctness. This step ensures your solution is both efficient and scalable, making it suitable for large inputs. Key insights can further strengthen your algorithm design. First, understand the constraints provided in the problem. These constraints often dictate whether a simple brute force solution is feasible or if an optimized approach is necessary. For example, if the input size can reach up to 10 to the power of 6, a quadratic time solution would likely be impractical. Next, the choice of data structure plays a critical role in achieving optimal performance. A hash map, for instance, is excellent for constant time lookups, while a heap is ideal for priority-based processing. Balancing trade-offs between time and space complexity is another important consideration. Sometimes, using additional memory, like a hash set, can significantly reduce time complexity. When it comes to data structures, arrays are perfect for indexed access, while hash maps or sets excel in scenarios requiring frequent membership checks. Stacks and queues are ideal for specific patterns like LIFO or FIFO processing, and graphs are indispensable for network-based problems. Dynamic programming tables, on the other hand, are key to avoiding redundant calculations and problems involving overlapping subproblems. Selecting the right tools and techniques is essential for crafting efficient solutions. Let's explore an example to see these principles in action. Suppose we're tasked with finding the length of the longest substring without repeating characters in a given string, such as s equals abcap. We start by processing the string character by character, using a sliding window approach to track the current substring. A hash set is used to store characters in the current window, ensuring we can quickly detect duplicates. If a repeating character is encountered, the left pointer of the window is moved forward to exclude it. After each iteration, the maximum length of the substring is updated. For this input, the longest substring without repeating characters is ABC, with a length of 3. This example highlights how combining data structures like hash sets with techniques like the sliding window can efficiently solve the problem while adhering to the constraints. This code solves the problem by utilizing dynamic programming to count special subsequences. The DP array tracks the number of valid subsequences ending in 0, 1, and 2, respectively. The problem constraints allow us to process the input array nums in a single pass. The variable mod ensures that results remain within the specified modular arithmetic bounds of 10 to the power of 9 plus 7. Each element in the array is processed as follows. 1. If the current number is 0, all existing subsequences ending in 0 can either include this new 0 or not. Hence, the count of subsequences for 0 doubles, and we add 1 for the new single-element subsequence, 0. 2. If the number is 1, it can either extend subsequences ending in 0, forming new subsequences ending in 1, or not. Therefore, the count of subsequences for 1 doubles, and we add the current count of subsequences ending in 0. 3. If the number is 2, it can extend subsequences ending in 1, forming new subsequences ending in 2. Thus, the count of subsequences for 2 doubles, and we add the current count of subsequences ending in 1. At the end, dp2 contains the total count of special subsequences ending in 2, which is the desired result. This approach is efficient with an O(n) time complexity and O(1) space complexity. This is the Java implementation of the given Python logic. The solution uses an array dp to track the counts of special subsequences at each stage, with modular arithmetic to prevent overflow. Key differences include explicit type declarations, usage of int and long for numerical computations, and the use of a for each loop for array traversal. To begin, let's look at the first example where the input array is 0, 1, 2. Initially, we set up our variables. Nums holds the input, dp is an array initialized to 0, 0, 0, to keep track of subsequences ending with 0, 1, and 2 respectively, and mod is set to 10 to the power of 9 plus 7 to ensure results stay within range. Now, for the first number, 0, we update dp 0 using the formula 2 dp 0 plus 1% mod. Since dp 0 is initially 0, this calculation gives us 1. So, dp becomes 1, 0, 0. Next, for the number 1, the formula for updating dp 1 is 2 dp 1 plus dp 0% mod. Substituting the values, we find that dp 1 becomes 1, resulting in dp being updated to 1, 1, 0. Finally, we process the number 2. Here, we apply the formula 2 dp 2 plus dp 1% mod to update dp 2. Since dp 1 is 1 and dp 2 is 0, the result is 1. This updates dp to 1, 1, 1. With all numbers processed, the final value of dp 2 is 1. Therefore, the result for this example is 1. Now, let's explore the second example where the input is 0, 0, 1, 2. We start with the same initial setup. Nums holds the input, dp is 0, 0, 0, and mod remains 10 to the power of 9 plus 7. First, we process the number 0 using the formula 2 dp 0 plus 1% mod. This gives us dp 0 equal to 1, so dp becomes 1, 0, 0. When we encounter another 0, we update dp 0 again using the same formula. This time, substituting dp 0 as 1, the result is 3. Thus, dp is updated to 3, 0, 0. Next, we process the number 1. Using the formula 2 dp 1 plus dp 0% mod and substituting dp 1 as 0 and dp 0 as 3, the result is 3. This updates dp 1 to 3, making dp equal to 3, 3, 0. Finally, for the number 2, we calculate 2 dp 2 plus dp 1% mod. Since dp 1 is 3 and dp 2 is 0, we get a result of 3, which updates dp 2 to 3. The final dp array is 3, 3, 3, and the result for this example is 3. In the third example, the input is 0, 1, 1, 2, 2. Starting with our initial setup, nums holds the input, dp is 0, 0, 0, and mod is 10 to the power of 9 plus 7. For the first number, 0, we calculate 2 dp 0 plus 1% mod, which results in 1. So, dp becomes 1, 0, 0. Next, for the number 1, we use the formula 2 dp 1 plus dp 0% mod. Substituting in the values, we find that dp 1 becomes 1, updating dp to 1, 1, 0. When we process another one, we use the formula 2 dp 1 plus dp 0% mod again. With dp 1 as 1 and dp 0 as 1, the result is 3. This updates dp 1 to 3, making dp 1, 3, 0. For the first occurrence of 2, we calculate 2 asterisk dp 2 plus dp 1% mod, which gives a result of 3. This updates dp 2 to 3, resulting in dp being 1, 3, 3. Processing the second 2, the formula 2 asterisk dp 2 plus dp 1% mod is applied again. With dp 2 as 3 and dp 1 as 3, the result is 9. This updates dp to 1, 3, 9. The final value of dp 2 is 9, so the result for this example is 9. The time complexity of the algorithm is determined by the operations it performs as it processes the input array nums. First, the algorithm iterates over the entire array using a single for loop. Since each element is visited exactly once, this contributes n to the overall time complexity, where n is the length of the array. Additionally, for each element in nums, the algorithm updates the dp array. These updates involve constant time operations, such as arithmetic calculations and conditional checks, which are O1 per element. Because these operations are performed once for each of the n elements, their contribution is O1 asterisk n, which simplifies to O(n). When we combine these, the total time complexity of the algorithm remains O(n), as no additional operations increase the growth rate. Now, let's analyze the space complexity of the algorithm. The space usage primarily comes from the dp array, which is fixed in size and contains 3 elements to store intermediate results. Regardless of the size of the input array, the dp array always requires constant space, making its contribution O(1). Other variables, such as the mod constant and the loop variable, also consume a negligible and constant amount of space, which does not grow with the input size. Since the algorithm does not allocate any additional memory or data structures that scale with the input, the overall space complexity of the algorithm remains O(1). This efficiency in space usage is one of the reasons the solution is optimized. When comparing this approach to a brute force solution, the advantages of the optimized algorithm become clear. A naive method would generate all possible subsequences of the input array nums. Since each element can either be included or excluded, this results in 2 to the power of n possible subsequences, giving the brute force method a time complexity of O2 to the power of n. Additionally, filtering and counting valid subsequences would add even more overhead, making this approach impractical for large inputs. In contrast, the optimized algorithm avoids generating subsequences altogether. By leveraging dynamic programming, it maintains counts of subsequences ending in specific values and processes the input in a single pass, achieving a time complexity of O(n) and a space complexity of O(1). Whether in the best, average, or worst case, the algorithm consistently iterates through the input array once, updating the dp array as it goes. This ensures that the time complexity remains O(n) across all scenarios, making the solution scalable and efficient. To mathematically validate the time complexity, we can represent the algorithm's execution time as Tn, where n is the size of the input array. The algorithm includes a single loop that iterates over all n elements, and for each element, it performs constant time operations, such as updating the dp array. This can be expressed as Tn equals c asterisk n plus c underscore 0, where c represents the constant time for operations performed on each element, and c underscore 0 accounts for any fixed overhead, such as initialization. Since constants do not affect the growth rate as n becomes large, we drop them, leaving Tn equals O(n). This confirms that the time complexity of the algorithm is indeed linear in relation to the size of the input. When solving string-based problems, there are several common mistakes that can trip you up if you're not careful. One major issue is failing to handle edge cases, such as empty strings, single-character strings, or strings with repeated characters. These scenarios might seem minor, but they can cause your solution to break if not properly accounted for. Another frequent mistake involves incorrect indexing in loops, particularly in sliding window or two-pointer approaches. For example, if you're using a two-pointer technique and forget to update both pointers appropriately, it could lead to infinite loops or incorrect outcomes. Additionally, relying on inefficient algorithms, like brute force, might work for small inputs but will fail for larger ones due to time complexity concerns. For instance, an O(n) squared solution is unlikely to pass time limits when an O(n) approach exists. It's also crucial to pay attention to problem constraints. Overlooking these can lead to unnecessary complexity or incorrect assumptions. Lastly, when using iterative techniques like dynamic programming or backtracking, always ensure you're resetting states or variables between iterations. Forgetting to do so can result in errors, especially when reusing data structures across iterations. Now, let's talk about insights that can help you during interviews. Pattern recognition is one of the most critical skills to develop. Many string problems, especially those involving sliding windows or two-pointer techniques, follow common patterns. By practicing these, you'll learn to quickly identify which technique to use for problems like substring or subsequence manipulation. Also, before diving into your implementation, take a moment to think through possible edge cases and constraints. This upfront consideration can save you a significant amount of time and debugging later. It's equally important to clearly explain your thought process during an interview. For instance, if you decide to use a sliding window approach, articulate why it's suitable for the problem and how it optimizes complexity. Additionally, be ready to discuss trade-offs in your solution. For example, while an algorithm with lower time complexity might use more memory, you should explain why the trade-off is acceptable given the constraints of the problem. To deepen your understanding of these concepts, it's helpful to practice related problems that build on similar techniques. For example, LeetCode Problem 3, longest substring without repeating characters, is a classic sliding window problem that focuses on substring manipulation. Another great example is Problem 76, minimum window substring, which emphasizes the use of sliding windows paired with hash maps for substring matching. Problem 424, longest repeating character replacement, also uses the sliding window approach but incorporates character frequency to solve the challenge. Finally, Problem 567, permutation in string, requires checking for permutations with sliding windows and frequency maps. These problems are excellent practice to strengthen your grasp of common patterns and their practical applications. Finally, let's consider some alternative approaches and their trade-offs. The brute force approach, while straightforward to implement, often results in time complexities of n squared, or worse. This might be acceptable for smaller inputs but will struggle with larger constraints. A more efficient option is the sliding window technique, which often reduces complexity to n. However, implementing this correctly requires careful pointer management and attention to edge cases. Hash maps or frequency arrays are another powerful tool, particularly for problems involving character frequency or anagram checks. The trade-off here is increased space complexity, which might not be ideal for all problems. Dynamic programming is another effective approach, especially for problems involving subsequences or overlapping subproblems. While it can significantly optimize solutions, it can also be more challenging to implement and debug. Each of these approaches has its strengths and weaknesses, and it's important to choose the one that best aligns with the specific constraints and requirements of the problem at hand. Great work! We've summarized the key points from this problem and discussed its optimal solution. Remember to focus on understanding the requirements and choosing efficient approaches for similar challenges. Don't forget to like, share, and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!